Well, hello and welcome again to our journey into linear algebra, and we've been looking at orthogonal transformations in 2 dimensions and then in 3 dimensions, and we're going to look now at what happens to reflections and composites in 3 dimensions. So we know that an orthogonal matrix has to have determinant plus or minus 1. You should make sure you know how to prove that. It's fairly simple. And we know that if the determinant is plus 1, it's going to be a rotation. But what happens if the determinant's minus 1? Well, it won't in general be a rotation, so we'd like to know what it is. And we saw earlier that an isometry can be represented by an orthogonal matrix. An orthogonal matrix preserves lengths and angles. That is, an orthogonal matrix is an isometry. So we also know that this is true for rotations. Is it true for any other linear geometric transformations? So I'm going to take this very simple Q, which is a 3 by 3 matrix. It looks like this, and it's pretty obvious the determinant is minus 1. So I'm going to take Q to be any 3 by 3 orthogonal matrix with determinant minus 1. I'm going to let M be this matrix, which clearly has determinant minus 1. And then it's fairly obvious that if you square this one, you're going to get the identity, so it's its own inverse. And if you multiply Q times M, Q is any 3 by 3 orthogonal matrix of determinant minus 1. And you multiply these together, you're going to get an orthogonal matrix with determinant plus 1. So that means this composite Q times M, which I'm calling R, is a rotation matrix. And that means this Q, I can now multiply both sides by M inverse, which is M. So Q is Rm. And so that means for any vector v in R cubed, we can write QV is Rm times v. And the action of Q on v then can be divided up into 2 stages by simply looking at this here. So firstly, when I multiply M times v, algebraically, all I'm doing is I'm making the first component of the vector v change signs, and geometrically, therefore, this represents a reflection in some plane through the origin perpendicular to the vector E1. Now that's what M does to V, and then after it's done this reflection, R is a rotation matrix, and so R is then going to rotate. So second, the resulting vector MV is now rotated through some alpha about the z-axis, about some z-axis. That is, we can conclude now that an orthogonal matrix with determinant minus 1 represents a reflection in a plane followed by a rotation. So if the determinant of our 3 by 3 matrix is plus 1, it's just a rotation. If the determinant is minus 1, then it's a reflection, then followed by a rotation. And we state this in our next theorem here. The 3 by 3 orthogonal matrix with determinant minus 1 represents a reflection in a plane followed by a rotation about an axis normal to that plane. Well, obviously we'd like to find the equation of the plane and the axis of rotation and the angle. So given such a matrix Q, how do we find these things? Well, if V is the normal to the plane, then V is going to get sent to minus itself. It's going to just get reflected in the plane and go to minus V. And that means this vector V is an eigenvector corresponding to lambda equals minus 1. So we can then choose an orthogonal orthonormal basis. We'll put V1 to be our axis V, but made into a unit vector, and take two other vectors that making this into an orthonormal set. And then the matrix of Q with respect to this basis is simply going to look like this, because the first basis vector V gets sent to minus V, so its coordinates with respect to the basis will be minus 1, 0, 0. And again, the other two is going to be a rotation, and I get the little rotation matrix in here. Now, since Q, and I'm calling this R alpha minus, So since Q and R alpha minus are matrices of the same transformation with respect to different bases, they have the same trace. So the trace of Q is the trace of this, which is minus 1 plus 2 cos alpha. Notice a little bit different to the formula we had before, which was plus 1 plus 2 cos alpha. For these matrices with determinant minus 1, the trace formula is minus 1 plus 2 cos alpha. And from that, at least up to sine, we can find the value of alpha. So a couple of worked examples of this to grind through. So we take this matrix Q, which is 1/9 times this, and we're going to show it's orthogonal, determinant minus 1. We want to find the axis of rotation, the plane of reflection, and at least the cosine of the angle of rotation. So here's the worked solution to this here. Here's our matrix Q. Firstly, I leave you to check that Q transpose Q is the identity, which again you can just, if you like, check by just observing that the dot product of all of these is 0, any pair of them, and each one has length 9. So these are all unit vectors and they're all mutually perpendicular. So that's the same as saying Q transpose Q is I. And I won't grind through the determinant, but you can check the determinant of this one turns out to be minus 1. So what we've got here, we've got a plane of reflection and we've got an axis of rotation. So any vector is being firstly reflected in the plane and then rotated through an angle alpha about this vector v. So if v is the axis of rotation, then v is perpendicular to the plane of reflection. And when I multiply Q times this v, it's going to end up here at minus v. That means v is an eigenvector corresponding to lambda is minus 1 as its eigenvalue, and that means v lies in the kernel of Q plus I. So again, when we work out Q plus I, because of the 1/9 here, I'm really going to just add 9 to the main diagonal elements to get this one. Then I can forget about the 1/9. I do a little bit of just one elementary row operation here. The numbers are not that great, so I'm going to use the 1 to kill the 8. So I'll take this row minus 8 times this row, and that gives me 0 minus 36 minus 54. And I can divide this row here through by 9, so I might do that. So we get 13 minus 7 minus 4, 1, 5, 8. I'll divide this through by 9. In fact, I could divide it through by 18 is better, isn't it? So dividing it by 18, I get minus 2 minus 3. Now we want the kernel of this matrix, and so what I do is I look at the bottom row and forget what goes here for the moment, but I'm going to take 3 of those. That'll give me minus 6, and minus 2 of those gives me plus 6. So forget the 1 for the moment, because at the moment it's going to multiply by 0. So I'll need a 3 there and a minus 2 there, so that this dot products with this to give me 0. I go back to the next line, so I've got 15 minus 16 is minus 1, and to kill that I'm going to need 1 times 1 to give me 0. And then of course you check it on the top row. So the top row is 13 plus 8, which is 21, minus 21, 0. So this is in the kernel of this matrix. So this is the axis of rotation, or rather x equals to t times this is the equation of the axis going through here, the equation of the axis of rotation. Now the plane, it's easy to get the plane because what this v is a normal to the plane, and so it's a plane through the origin. So the coefficients here, the normal vector, give me the coefficients of the equation of the plane to which it is normal. So I get x plus 3y minus 2z, and it passes through the origin, so the right hand side is 0. Finally, if alpha is the angle of rotation, then we can take the trace of this, which is 1 over 9, and that's going to equal minus 1 plus 2 cos alpha. And I'll just check I've done that correctly. So if I take that across, I get 10 over 9, halved, you get 5 on 9. So cos of alpha is 5 on 9, and it's unique up to the sign. We're not sure whether it's plus or minus the inverse cosine of this. So that's one example of that. Always like to do perhaps some couple of examples of this. So we're having a look now, and we're going to show that this matrix 1 in 15, 10, 11, minus 2, minus 10, 10, 5, minus 5, 2, minus 14. We want to show that this is a matrix of reflection combined with a rotation. We want to find the plane of reflection and the axis and angle of rotation. So good idea was to stop the video at this point and do it yourself, and then check that you've got the same answer as I got. So you might like to do that. I'll continue on with the work solution to it. So here is the matrix Q that we started with. Again, you need to check that by hand that Q transpose Q is I, and the determinant of this is minus 1. You can check that yourself by hand. Again, we take the axis, so that means we want, if QV is minus V, then V is in the kernel of Q plus I. Now, because of the 1 in 15, we're going to add 15 to the main diagonal, which gives me this matrix. And we want the kernel of this matrix. And what did I do here? I used the minus 5 to kill these above, so I took this plus 5 times that, and I took this minus 5 times that, which gave me this matrix. And you can see from, say, looking at the top row, if I take one of those and minus 7 of those, then that'll kill that one, so that will be dot product with 0 to give me this one. This is the same, and then I use the bottom row to get the number at the top. So at the moment I've got 2, minus 7 is minus 5, so I need plus 5, so I need minus 1 lots of that one. And I've got too many minuses here, so I'm just going to say that's the same as the span of 1 minus 1, 7, just to make a few less minus signs. You can work with this, of course, doesn't matter. And then the axis of rotation then is 1 minus 1, 7 times t. The plane of reflection we get by simply using the coefficients here, and it passes through the origin. And the angle, we need to go back and get the trace. The trace of this is 6 on 15. So the trace of Q is 6 on 15, which is minus 1 plus 2 cos alpha. Take this across, you get 21 on 15 divided by 21 on 30, and I just divided top and bottom by 3. So cos of alpha is 7/10, and it's unique up to sine. Finally, we can, if the angle of rotation could be 0, and so we could end up so here I just mentioned that here, as in the case of rotation, finding the sine is somewhat harder, but can be done using by following the method that I mentioned above. Now, in this kind of problem, it could work out that alpha, the angle of rotation, could turn out to be 0, in which case the matrix represents what we call a pure reflection. So there's a reflection but no rotation. And just as a final example of this, here's a matrix Q. We're going to show this as a pure reflection and find the plane of reflection. So all we're going to do here is, in the solution here, here's our matrix Q. And again, we've got to check that it's orthogonal, check its determinant is minus 1. I found the axis of rotation in the usual way, so I find the eigenvector corresponding to lambda is minus 1. So here I've added 17 to the main diagonal, and then what have I done here? I had a minus 12 here and a minus 12 here, so I've just subtracted the two rows to get me a 0 here. Once I've got 1 0 in here, you can write down what the thing is. So this middle row says I could have one of those and minus one of those. However, you then have to introduce fractions to work out the third entry, so I've taken 2 of those and minus 2 of those. And then if you look at, say, the top row, you take twice that one, which is 52, minus 16, which is minus 36, so you need minus 3 times the minus 12 to give you 0, and you can check it on the bottom row that it works. So you get, what do you get here? You get 24 plus 24 is 48, and then minus 3 times 16 is 0. So the equation of the axis then is 2 minus 2 minus 3, and the equation of the plane then is 2x minus 2y minus 3z is 0. Now to show it's a pure reflection, we've just got to show that the angle is 0. So if alpha is the angle of rotation, then the trace of q, if we go back to q, what happens here? We get 9 plus 9 is 18, minus 1 is 17, on 17 is 1. So the trace of q turned out to be 1, and then that's equal to minus 1 plus 2 cos alpha, and that gives me cos alpha is 1, and the cos of 0 is 1, so alpha is 0. And so q then is a pure reflection. And that is the end of this section.